Hello and welcome to episode 006 of Poor Man's Electronics Bench. In this episode I am going to go over my acquisition of a Hewlett Packard E3612A power supply. This particular power supply is a 0 to 60 at 1/2 amp and 0 to 120 volt DC at 1/4 amp, 0.25 amp. It's a handy supply to have on the bench. I've noticed that there's been quite a few on our favorite auction site, some of them going for a higher dollar value. This one I obtained at a pretty reasonable cost. It's got some cosmetic damage to the face. It's got a little rip on it. It's not a deal breaker, of course, and then it's also missing a knob. I've got a plan for the knob I'll probably go over with at the end of the reassembly and calibration on it. I got the unit and I've already inspected it. It is in working order. I actually used it on one of the other videos for a power supply. I did do some historical research on it, and I did find out that there is an issue that has popped up that a couple other content creators have had with this particular power supply. It might apply to the whole line because this line actually covers a E3610, E3611, and E3612. They are three different maximum voltage power supplies. What's been happening is there is one particular capacitor in a power supply section that has basically failed and puked its guts all over the printed circuit board with the ongoing damage from whatever the electrolyte chemical is to the board, and people had to go through some pretty good lengths to remove components, clean things up, put it back together, and hopefully there's no leakage in the board. I think both of them got the items going, but causing more problems than it should have. And I'm going to go over what I seem to have found might be an issue in the schematic and the actual design and assembly of this unit for that one power supply capacitor. What's been happening, it seems like, is that capacitor might be underrated for its actual task, but we'll go over that, and probably out of my reassembly and doing a recap on this thing, which I plan to do because I'd like to keep it in good working order, and this one does not have damage to it. I'll go over load testing it and checking before and after I replace that capacitor to find out if in fact there's some kind of design flaw with it. This unit is particularly easy to get into. It involves no screws. You'll just need a flat blade screwdriver. I'll go over that with you in a second because I'm going to reposition the camera. Okay, I'm back. The unit is unplugged and depowered. It does have a standard IEC socket in the back, fuse holder, fuse rating. It's not exactly laboratory quality, but it's fairly good quality as far as bench equipment goes, and it has spots top and bottom. There is a plastic ring along the whole assembly on the back, and then also on the front. The front cover kind of holds and clamshells the top and the bottom covers together. So I'm going to go over just getting in there. You'll need a small slotted screwdriver. Shouldn't have to apply too much force. It basically almost, you stick the screwdriver in just about and it wants to come out. I try to do the bottoms first to take the stress off the top. That's my plan anyways. I don't know how well it works, but like if you get both of them started on the bottom, flip it back over, as far as this assembly goes, it's as easy as you can get. Just have to be fairly careful with the screwdriver. Okay, clip is off. What this will allow is for the upper and lower covers to clamshell off. And the front panel will actually detach quite a bit. The buttons will come out. And it's got some, just got a ribbon cable that can be disconnected if it's kind of tight. I'll try and leave it. But the front panel does accordion off a bit. The back seems to slide in with this heatsink assembly here. It's got a slot top and bottom, so I'm probably, there we go. Just take the weight off it. And the nice thing about this is it looks like, well, it probably, if the front panel got totally in the way for some reason, you have 8 connectors to desolder off the board, 1 multi-connector pin to take off, and you can deal with everything without having the front panel on, or you can leave it. The front panel also does have a slot to support the board in, so it actually might not be a bad idea to leave it on, except for having some, you had to get to some solder joints along the front edge here, but it's in really pristine shape, or fairly pristine considering it's just aged. I did notice one strange thing though. It's got, I'm gonna have to correct the cover on the case here. There is one spot on the board. It is right here, and it's got a little mechanical abrasion on it, and I've noticed that on the bottom cover that happens to line up with this little pin right here. And the funny part about it is, if you look at the pin, I don't know if you can see it from the camera angles, but you can actually see depressions from the printed circuit board trace that it's going over in this plastic pin. So I guess in the mechanical business you would call that an interference fit, but we're going to cut that pin down. It really doesn't serve any function being there. I really couldn't even call it a good support for the board, especially if it's going to dig into the circuit board trace and damage it. So I'm going to cut that bottom of that pin down, and everything else, there's no other signs of abrasion or anything on it. It's in nice shape as far as printed circuit boards go. And the components themselves are fairly straightforward. There's some set value plus minus 12 volt, 5 volt rectifier, small bridge rectifier, some adjustable trim pots. You have some capacitors to filter out the smaller value rectifiers. There's not a lot of capacitors, there's some, and there's one larger one. So out of this inspection, I'm going to measure up all my capacitors for physical sizes and then order replacements for them. But I think it is this particular capacitor, there's 2 capacitors that are here. There's a C13 that is this one here, and then below it a little bit there's this one, and I think it's this one down here, but I will put little excerpts that's a C7. One of these capacitors is only rated for 35 working volts. The other one is rated for 50 working volts. The odd thing is they are plus and minus, they're on a plus and minus 12 volt center tap winding off of either one, and for the life of me I can't figure out. It's almost like it's, a mirror image circuit for rectifier circuits. You got a plus 12 volt and a minus 12 volt. Then you've got a LM7805 chip that's on there, that's off of a voltage divider to put out a 5 volt output as well, but that's off the 12 volt side. But that the plus 12 volt side has a capacitor with a 35 volt working voltage rating. The minus 12 volt side has one with a 50 working volt rating. And the one that's been failing is this. It's this one. I can see it right here. It's a 330 microfarad at 35 volts. I don't know if I can get this on the camera here. I have to take the camera out the cradle. But that particular one is a 330 at 35. And the other capacitor is a 470 at 50. But this one is carrying, the 470 at 50 is carrying the minus 12 volts. I really don't know why they put a smaller rated capacitor on two sides, or or somebody just fell asleep at the wheel or goofed up and designed it, put it on paper, factory said okay, built it, sent it out the door, and then people are having problems with them. But at this point I'm going to go over the two excerpts from two other YouTube technicians' content site that both had issues with that C9 capacitor, and then I'm going to go about my plans for what I'm going to do about replacing said capacitors. But in the meantime also I'll probably do a load test just to see if there's any excessive ripple on the existing configuration before and then also after. So that's my plans for this video, so stay tuned and we shall go forward from. I have some screen captures from the two other content creators' sites. The first one was Duality Repair. I have the listing for the name of his video, as well as I will include a link to their videos in my description. And I thank them very much for their help and their content. I just want to also let them know that I do not have my account set to make any profit off of these videos at all. I'm not mining any bitcoins or any US dollars out of any of this. This is doing this for information sharing so others can have this information out available to use. So the first one is the Duality Repair, and he's pointing out the C7 capacitor that has failed and leaked on his board. It's right pretty much center screen. I've got it indicated over here. And then the other one is Toltec Merck, who had the exact same issue on the exact same E3612 unit. It is also the C7, and both of these capacitors failed to the point where they leaked electrolyte up and down along the transformer and caused both of them, I think they have to remove parts to do a cleanup on the board in order to cut down any type of leakage between components before they can complete their repairs. I'm lucky enough where my C7 or none of my electrolytic capacitors leaked, so that part's not an issue for me, but I'm looking to avoid that by changing the capacitors for one, and for two, to see what happens if I match my two values for my plus and minus rails with the same size, capacity, and voltage rating capacitors, which probably should have been done from the factory to begin with. So we will continue on from there with a description on the schematic as to what's going on. Here is a good blown up view of the power supply section for the one part of the E3612. This board seems to be the same for the 3610, 3611, 3612, since it's all constant voltage, constant current supply sets, which are all going to be the same function inside the unit. The only difference is going to be mostly the main output power voltage levels and transformers associated with it. It's a little blurry zooming in. It's not the best copy. I can try and get a better copy later, but I'm going to go over with you. You got a center tap transformer that's rated, I don't know, I'm guessing it's a plus or minus 12 off the center tap, 24 volt total, that's what they're trying to achieve, but I'm not exactly sure because I didn't take a power measurement on it yet. It's got a full weight bridge. Then going in, you've only got basically what's LM7812 and LM7912 for the negative, plus or minus negatives. If you look at the positive side, this one here is a C7. It's 330 microfarads at 35 volts. If you look at the negative side, C13, that's 470 microfarads at 50 volts. So why they, and then going through the regulator, you've got capacitors on your output side, 1 microfarads at 50 volt also. These are 50 volt rated. I can't understand why these three capacitors are all 50 volt rated, and even these small 0.33 microfarad capacitors, are 50 volt rated, and this is only a 35 volt rated. I just don't understand it. And the thing is, that seems to be the particular capacitor that's failed for at least 2 people that have repaired these units. It's, clearly visible. It's the exact same capacitor that's failed. And the thing about this positive rail too is it's got more of a load on it because you've got a voltage divider network, the Zener diode on it, and it's got a +5 and a +12 voltage output source that goes to supply other parts of the board. It seems like for better ripple stability and just better voltage control in general, why you don't have a 50 volt capacitor, why these two capacitors aren't basically mirror image of each other, I don't understand. And I'm going to pursue, for one, checking this thing at close to its full load on the ripple with these original capacitors installed, and then I'm going to change out this other capacitor and do the same test full load just to see if it does make a appreciable difference. But the thing is, it's definitely making a difference in design as far as a failure on this board. I don't understand why they chose to do what they did, but I guess we have what we have. So as technicians that are stuck with these units, we either have to wait until the capacitor pukes and repair it, or possibly do something beforehand. That's the dreaded recap. But I'd rather, in a situation like this, I'd rather recap things beforehand than wait until something gets damaged, and then have to go back in, clean the board up, pull other parts out, and go through a whole bunch of other work when I just could have unsoldered one component and soldered in another one. So that's my plan for now. So we'll go forward with sizing up the capacitors for an order, and then going through and doing the actual testing of the existing configuration, replacing the capacitors, and then testing it afterwards. And I'm back, and I'm just going to go over sizing up capacitors for the recap. I don't know how many people have done this before. I'm sure probably some people watching this have probably done it routinely. I don't know how involved they get, or if they just order, make guesses, or what they do. I'm going to go over a little bit of the way I do things. I keep track of everything in a spreadsheet as far as the capacitor number, the values, and then the two main things I'm concerned about is the diameter of the capacitors and the lead spacing in most instances, because between the time that these original capacitors were made and the current day, it's over 30 years usually, and the size of the capacitors available for these same values are a lot smaller than what's been installed in most pieces of equipment. So the main thing you have to watch out for is just to make sure that your leads are going to be long enough and that you're ordering them in the right configuration. Most electrolytic capacitors are available. The majority of them are going to be either surface mount or radial leads. There's axials available, but they seem to be a lot more expensive for the same value. And if you could get something with radial leads that's can make the reach for the axial leads, it's probably going to be a better value and a more available source of replacements as far as different manufacturers and quality values for what you're looking to replace. So I'm going to go over the main one first, the the big C2. This is a 1000 microfarad at 250 volt. The capacitor body itself is a 35 millimeter. And then we want to document our lead spacing for a replacement. I think I checked this before. It's probably going to be might cause some problems. It might be a snap-in, and those snap-ins have bigger leads, so might have to modify the capacitor itself, but the value on that is about a 10 millimeter from spot to spot. So basically it's just going through and documenting all that to make sure that the capacitors that you're ordering are going to fit on the board fairly well. It's a little bit of a time-consuming process, but it does help for the quality of your reassembly when you're going to stick your new parts in. We'll just make sure that the parts fit a little better and give you less of a hassle on the way through doing things. So at this point I'm going to take a break from this video, make a capacitor order, and the main reason I'm doing this is a going forward video also is because I missed at least one value resistor on my ICO 443 semiconductor curve tracer that I need to order the part for. So I figure instead of just ordering one resistor from a supplier that charges $5 or more for shipping for items, I'd like to make another order for another device to get something else going next. So that's my plans, and we'll be back to this one soon. And thank you for watching, and I hope that you've got some information out of this. If anybody has one of these units, what to look out for, why things are happening like they're happening, and what can possibly be done about it, and also what the results are from upgrading capacitor values in that particular power supply section. So again, thank you for viewing, and hope to see you soon. This content is available on YouTube and Odyssey.com. If you enjoyed this, please like and subscribe. Hope you return soon.